Welcome back to learning module number 7, part 2, where we will consider cathodic and anodic protection. Allow me to go back to one of the slides where we mentioned it early on. That was right here. I'm going to use this slide to explain a little bit more about cathodic and anodic protection. I highly recommend you to familiarize yourself with each and truly to understand each at depth because they are extremely powerful and they're also most commonly used in the industry, especially if you ever plan to join the corrosion industry. Now, first, I would like you to understand the difference between cathodic and anodic and never swap them, right? Well, in cathodic, the metal that we protect serves as cathode. Okay. Now, in anodic protection, the metal that we are protecting serves as anode. Okay. So I'm going to say the metal we protect is cathode, right? Now, in anodic protection, the beauty there is that you allow your metal to be an anode. And first, I will remind you, back from the galvanic cell, we know that in the galvanic cell, whenever you have an anode and cathode, anode what corrodes. So in cathodic protection, we don't allow our material to be the anode. We do something around it to make it the cathode. And because it's a cathode, it doesn't degrade. Okay. Now, in anodic protection, we allow our metal to remain as anode, but we do something to it to quench its corrosion or to minimize it to an extremely low value. Now that you know that, right? So the name comes basically from the role of your metal, right? Your metal is either a cathode or it actually an anode. Let's begin with the cathodic protection. Okay, so back to the galvanic cell. You guys remember that whenever I have an anode and the cathode, the anode corrodes, right? And the way you can describe it is that you know that there is this reaction happening, right? You have a dissolution of metal, meaning that metal, the electrons flow from the anode to cathode, right? And that's why anode degrades, okay? And the anode dissolves. This is why the scientists were like, wait a second, what if I just flip the current? What if I send my electrons toward the metal? Would that stop the corrosion? Yes, it will, right? Because if you're sending the electrons toward your metal becomes the cathode. And there are a few ways to achieve it, right? Okay, so once again, cathodic protection is achieved by supplying electrons to the metal structure to be protected. So you always have like this galvanic cell. With cathodic protection, you have the galvanic cell. But what you do is that you just ensure that the electrons flow toward the metal that you're trying to protect. Because when that happens, that means that your material plays the role of the cathode. And this is why we call it cathodic protection, right? Now, how it helps? Well, the addition of these electrons, right, that are blasting the metal tend uh, tend to suppress the metal dissolution, which is the dissolution is going to be basically it's this reaction and you're trying to reverse it, right? You're quenching the loss of electrons because you are adding them. You're kind of like pushing it back. You're suppressing the metal dissolution. And as such, you also increase the rate of hydrogen evolution. This would be happening, right? Well, because if I'm reversing the reaction, right, the other reaction would increase, right? So this is why with cathodic protection, you must be beware of hydrogen attack because that can become an issue. While we're using the galvanic cell concept to protect our cathode, right? But now because it's a cathode, right? You can end up with hydrogen generation and hydrogen now becomes a concern, right? But there are ways to get rid of it too, because you already know that whenever you have this hydrogen concern, right, you can use coatings, you can use inhibitors. You just try and use the metal that allows you to just put a barrier between the metal and the hydrogen, right? Now, a very, very important point, and perhaps I'm going to switch to red to emphasize it, is that the structure is protected only if the current enters from electrolyte, right? And that is paramount. And I will show you the examples. And there are two ways to supply the electrons, okay? So the electrons can be supplied from the electrolyte by an external DC output and by galvanic coupling to a more anodic metal, and we usually call it sacrificial anode. For simplicity, I'm going to start with the method number 2, where we're using a sacrificial anode because I think it's the easiest to grasp and to actually make sense out of it. And to give you an example, I'm going to give you an example of a domestic hot water heater, right? They all use a sacrificial anode. So this is going to be a cathodic protection using a sacrificial anode, extremely common technique. This is a water heater in cross section, right? So imagine if somebody cut it through, and that's exactly what you would see inside. So I want you to think of the following. The water heater, right, which is going to be the walls right here, I'm going to highlight it in red. It's important. It's made typically out of steel, okay? And I want you to think of the following is that the water enters the water heater, right? The water heater heats it up, right? And then obviously it stays there at a high temperature. And then if you consume a little bit, it gets replenishes. But I want you to, for a second, to envision that, oh my God, water heater usually serves you up to 10 years, right? But if you think about it, this is a hot temperature to begin with, and you have water inside, and of course water has a certain amount of oxygen dissolved in it, so you're basically looking at something that should degrade, right, and should degrade fast. But in the meantime, we don't replace the water heaters often, right? Typically once every 10 years. How do they achieve it? Well, because if I am to just have the structure where I have my steel tank with water inside, with very hot water, I will have corrosion, uniform corrosion happening all over my heater tank. That is unavoidable. How can I stop it? Well, I can take something that is more negative with respect to steel, and actually I'm going to take something that has a very high tendency to corrode, and that is going to be magnesium, and I'm going to install it into my tank, and I will make sure that these two are in direct contact. And what's going to happen is that I have now two electrodes where steel now becomes your cathode. And that's the key word here. That's why it's cathodic protection, because I put something in there which acts as the anode, meaning that as the time goes by, that bar, that magnesium bar, will slowly disintegrate due to the galvanic corrosion. And we call it a sacrificial anode because I intentionally sacrifice that bar so I can protect my heating tank. Now, with that being said, whenever you buy a heating tank, they give you the warranty and they say, well, it include. I'm going to throw random numbers at you guys. Last time I bought it, I didn't even look up the numbers, but they always tell you, okay, we're giving you this 3 years, but you can buy additional for $200. You can buy additional 2 years. Let me tell you. Every tank has the same magnesium anode. By buying additional insurance, they're not putting a larger bar in there that will last longer. It comes from exact same manufacturer, and there's the same weight of your anode, right? There's the same chunk of the magnesium that is installed in there, right? So what's going to happen is that you are guaranteed to protect, let's say, up to 5 years, but they will never sell you for longer than whatever they know they have it protected for, right? let's say if they know that this magnesium anode will only last for 5 years, that's the only insurance that they will give you, right? They will give you 5 years and not more than 1 day. Because beyond that point, once the magnesium anode is gone, right? Once it disintegrated, once it got sacrificed, the next thing to get corroded is your tank. And that's why nobody's going to insure anything like that. So, is it possible to replace a magnesium anode? Well, absolutely. So, it's a good skill to actually have. And at some point, replace the anode. Because if you can do that, you will obviously enhance the lifetime of your tank by quite a bit, right? And on the outside, to prevent corrosion, it's usually covered with some kind of nice coating, right? Some kind of paint, right? Or a finisher that protects the outside from corrosion as well. So, to summarize, this is a cathodic protection using sacrificial anode. The reason I call it cathodic protection is because the material that I'm trying to protect serves a role of a cathode here. And the way I achieve it is I pair it in direct electrical contact with something that has a higher tendency to corrode, right? Now, and if you guys go back to the electron flow, what happens is that the electrons here, they move from the magnesium, right, to the steel, right? And that means that the electrons enter from the electrolyte to the steel, right? Because those two are in direct contact, and that is kind of like the important point. Okay, so that's the sacrificial anode. The second way how you can protect the metal is again using cathodic protection, but this time we're going to use impressed currents. Okay, and let me try to explain it. Okay, so here's how I'm going to do it. I do need to send the current toward my tank. So, and I'll give you guys an example. This is important. Let's consider that Dr. Morel has a tank full of oil. Let's call it my retirement plan, right? So I'm gonna put it underneath the ground to store, right? And once I'm ready to retire, right, I need to make sure that whatever the oil I have in there is preserved. So the way I'm gonna actually protect it is that I'm gonna connect it to the rectifier, right, which is basically your DC power, okay? And then I'm gonna have an anode right here, which we call a sacrificial anode. Not the sacrificial, it's inert anode, because in this particular scenario, we're using a bit different of a structure. It allows the current to go through it, but typically it lasts many, many years because it's considered inert, it doesn't corrode fast. And if I am to connect the way you guys see it right here to the rectifier, right? And it's important that I have a negative port here and a positive port here. Once I do that, that means that in this structure, I'm going to have a current that is going to be flowing through the soil toward my tank. Okay? And then, and this is, think about it, this is a bunch of electrons. So by assembling the system where you would need a structure that you're trying to protect, you would need a rectifier, right? Because it's going to supply the DC current. And then you need this anode. That now, think about it, is that my tank is getting blasted with the electron beam, right? And then that electron current, because it enters from the electrolyte to my metal becomes a cathode. It's one of the most common ways to protect. Usually, this is used for um, all the pipelines that run underground, right? It's also used for structures. Anything that's underground is usually protected by the impressed currents. It is easier to, once you install it, it is easier to, how we call it perhaps, to, I forgot the word, guys, when you are like, keep up with it. maintain it. Maintenance is pretty low, right? Because the anode that you have there is a bit different from the other anode we used to do that I've shown you in the previous example. It doesn't corrode there. The purpose it serves there is to conduct the electricity, the current specifically in the direction that we have. But okay, so my if I am to install everything like that, my retirement plan is safe and everything's going well. But imagine that I have a neighbor who had a pipe underneath my property and he never told me about that. And let's say this is his oil pipe, okay? And he never told me about this pipe. So when I had a team installing my tank and installing cathodic protection to my tank, right? He kept it secret. I did not know about his pipe. So what can happen is that a very dangerous example can happen. The current that you look at sometimes can escape the system, and you want the current to enter the exact path as I show it on the graph. But instead, imagine that there is few electrons seeking through, like they are leaking through here, okay? And I'm going to give it a name, stray current. Very dangerous. And because there is this metallic pipe, it's going to conduct this stray current and eventually it's going to leave the structure toward my tank, right? This is your electron, right? And the problem is proximity, right? The problem is that I never knew that the neighbor had a pipe. I did not report it. So the engineer that was installing the tank didn't discover it because it was maybe deeper, right? Maybe further away. We didn't see it when we were digging out to install the system. And what happens is that I'm sending quite a bit of current to protect my tank the way it should, but there is a portion of the current that actually we call it a stray current because it just escapes. Okay? And it enters his pipe, travels through his pipe, and then comes out somewhere next to my tank. So what's going to happen? And perhaps you want to pause the video and be like, okay, what's going to happen? And what's going to happen, obviously, to the pipe of my neighbor? And the answer here is that my neighbor is not going to have a retirement fund because the area where the electron leave the pipe is going to corrode because it becomes anode and it's going to corrode, right? And without knowing about that pipe, right, if we knew about that pipe, we would have chosen a different position for my tank, different placement. We would have put some insulation, right? We would have taken into consideration the knowledge of the possible straight current. But let's say in the scenario where we didn't know that, his pipe is gonna slowly and steadily corrode due to the system that I installed, due to the straight current. So whenever we do, so just to summarize everything I've shown here, again, the tank that I'm trying to protect and the impressed currents are most commonly used for all the underground structures. And again, the benefit here is that the anode that you have in the system, you just need a rectifier and the anode doesn't get consumed. It's an inert anode. The whole idea is that I just need to make sure that I supply my electrons toward my structure. And if the electrons enter from the electrolyte to the tank, my material becomes cathodic, right? It becomes a cathode, and then it will basically be protected as long as I have my supply of my current, right? However, whenever you install something like that, this is why it requires a lot of knowledge. It allows a lot of design. You have to be aware of anything metallic surrounding you, right? Because keep in mind is that you often may have a stray current. A stray current, it's basically like a stray dog. It's a current that leaves off the pathway and it goes sideways. And if it can enter a certain structure, right, and that structure will conduct it, the problem is that the spot, the area where the current is going to be leaving the structure is going to be your anode, right? Where it enters is going to be cathodic, where it leaves, it's going to be anodic. And that means that that structure is going to be compromised due to the corrosion by the impressed current. Okay, so I do want you to really understand this too. Typically, in my experience, students are exceptionally well. They understand the concept very well when it comes down to the sacrificial anode because it kind of makes sense. Just slap these two together, right? And whatever we sacrifice one, but we don't care. That's intentionally. But whatever we need to protect will get protected, right? And of course, I will give you guys examples of many of this usage of sacrificial anode. If you plan to go outside and if you plan to travel on a boat, or if you don't have to travel, if you have a boat that you store in water, right? It's standing in water. You can just take, depending on what your boat is made of, but let's say it's made out of some kind of steel. So I'm going to take a chunk of either aluminum or I can take magnesium. Both of those will work. And I'm going to stick it to the bottom of my boat. And that bar will intentionally, preferentially corrode while protecting the rest of my boat, right? So sacrificial anode makes sense, but I really want you to also understand the impressed current because if you are to join the industry, you would encounter cases like that, and you would be a part of the engineering team that have to first sit down and design the system, right? After you study, obviously, the environment where you have to install it, then you come back, you design it, and then you go back in the field and you install it. Now, I almost forgot. If any of you do get motivated enough to enter the corrosion industry, there is this company right here. It's called the madcore.com. They're pretty big and they actually share quite a bit of information and knowledge. They recruit a lot of engineers. Typically, they recruit people that first you have to be in the field. You have to be the person who doesn't design that. You have to be the person who installs it, right? But still, you have to be very trained to make sure that what you are installing actually makes sense, right? And I'm sharing here the link with you. You can see the video from their professional training where they train the junior engineers that just joined that have absolutely no corrosion experience, and they are being prepared to be out in the field to install different systems. And I think in that particular video, it's been a while, I don't really remember the content, but I do know that if you watch that video, you'll realize that, wow, I actually know quite a bit, and I am prepared to, jump in this field and contribute. Now, the second part of the protection is going to be the anodic protection. And I will remind you again, the key word here is anode. This time, the material that I'm trying to protect will be an anode. I will allow for the material to be an anode. So how and why would I do that, right? Because you would think that, well, anodes corrode, right? So how come if I let my metal be the anode, how can I stop the corrosion? Okay, anodic protection is very specific. It can only be applied to certain metals. Okay, and specifically, the technique is based on the formation of protective passive film. And so that means that you can only apply it to the metals that have this passive film. And hopefully you guys remember at some point when I was describing you polarization, and I'm just going to draw it right like this, right? If you guys remember, so this is going to be the current density, this is going to be my potential. Some of the metals are so unique is that there is within a certain range, right? They act as active. But if I keep increasing my potential, at some point, my metal goes into this state, let's call it a sleepy state, right? And it maintains this passivity, right? Inability to corrode. It basically becomes, oh my God, why would I do that? It becomes passive within a specific range. And then if you guys go above a certain value, it goes back to the active, right? So once again, and I'm going to highlight in here. So there is this area where material is active, but then within a certain range, and it's going to be, it will actually be slightly less than that, right? So I'm going to draw this up to which number? Up to here, right? So this is where the material becomes passive, okay? And then in here, it's back to active, okay? But this specific area is what I'm interested in because this delta E allows my material, it is an anode, but I'm going to apply a specific potential to it, and then I'm going to maintain my metal within that range. And in that range, my material is sleepy, right? It's very, very inert. So how would I do that? Well, very simple. So let's say if I have this steel tank, right? This steel tank, and I'm trying to protect it. And I will simplify the concept so it kind of makes sense. First thing first, I would need to use potentiostat, right? Because without potentiostat is a bit of an expensive technique. But what it allows you to have this reference electrode, right? So think about it. There's this reference electrode where you can measure the potential at, and then you measure the potential on a steel tank, okay? And now I'm going to take the difference between these two and I'm going to continuously measure it. And I just know that there's a certain range. Let's say I have to be, I'm not going to throw the random numbers at you, but let's say I will 0.5 to 1. I have to remain within this potential. So potential stat is the piece of equipment that allows you to continuously monitor the difference, the delta E, right? Because it takes two measurements. It looks at the reference electrode and then it looks at the tank that you want to protect. And then it basically compares the number. It measures the number, the difference. Then it compares to what is written in the software program, right? It says you have to be within this range. And then it either lowers the potential or increases the potential. And that's how the steel tank constantly exists within this range right here. I'll write it down again. You want to be here because the current density here is almost zero, right? And if the current density is almost zero, that means even though I have my anode, right, the steel tank here is the anode. There's no cathode, not partnering it with anything. But what happens is that the material does not corrode because you intentionally you basically gave it a chill pill and it's chilling there wherever you install it, right? It does take time to do the measurements properly, right? But once everything is set up, then, and of course it's costly, but once it is set up, you just know that the material will be protected, right? So to summarize things that I just said, now, anodic protection is used to establish a strong passive layer on the metal. So going back to my polarization curve where I was explaining, right? It's all about establishing this passive layer, but you have to keep in mind is that you can't establish a passive layer on any metal. That doesn't work like that. You need to begin with the tank has to be made out of metal. Like an example here is a steel that does establish active passive behavior, right? Now, this passive layer is going to mitigate the corrosion. And again, maybe back from when we were talking about the passivation, I did mention that people don't really know what this passive layer is made of, but we don't really care. Why? Because we found a way to use it, right? We don't know the nature of the layer. We would like to know it. Eventually, we will, right? But at this point, we just know the conditions at which that layer kicks in and exists, right? And that is what we use to basically already employ that passive layer, even though we don't really know what the passive layer is made of, right? Now, we use the potentiostat to maintain the metal at constant potential, right? And we do that with respect to the reference electrode. And once again, why you want to keep it at a certain specific potential, right? There's a range that is allowed, right? A safe range, because you want to keep the material pacified, right? And then typically the optimum potential is determined by electrochemical measurements, right? Sometimes you do the measurements, sometimes you just already know. Some materials are well studied, so it's relatively easy to figure it out. Now, if I am to do a comparison, right, I'm not going to go all in detail, but I want you to know something that you should remember for the rest of your engineering career, right? So if I am to compare cathodic and anodic protection, right? Well, first I know that with anodic protection, I actually allow my metal to remain as anode, right? And it's pretty ballsy, right? Because you know that anodes corrode, but I will intentionally allow my material to remain in that role. Why? Because I can only apply it to active passive metals, right? I can't apply it to everything. But cathodic protection, whether in press current or sacrificial anode, right? There are two. You can apply it to any metal. Now, corrosiveness, when it comes down to corrosiveness, anodic protection actually allows you, works extremely well from weak to very aggressive media, right? So it actually allows you to maintain the material safe in highly corrosive area. Whereas with cathodic, it is usually, the corrosiveness is usually has to be weak to moderate, okay? Now, the cost, the relative cost, installation and operation. The anodic protection, the cost of installation is very high because we would need to kind of like do the measurements and things like that. But then the operation is very low because if you think about it, there is not nothing gets consumed. You just need to make sure that the potentiostat works all the time and it's always in working order, right? Because numbers shouldn't be changing the range that you, if you properly designed the potentiostat value, then you don't need to come back and double check it all the time, right? And this is why it's the operation is very low, and perhaps it's a good investment for your structure that you're trying to protect. Back to my example with my retirement tank and the neighbor, right? If we knew that, let's say, the tank has to be here and his pipe has to be there, one of the ways to proceed is to actually install an anodic protection, right? Because that would allow my material to be an anode, right? And there would be no stray current. Now, when it comes down to cathodic protection, the installation is very low, and a lot of you who may either already own a boat or may own a boat in the near future, you'll be dealing with the cathodic protection. You'll be buying the sacrificial anodes and you'll be sticking them to the bottom of your boat if you wish your boat to serve a really, really long time, right? However, the operation, it's from medium to high. Why? Because, well, first, there are certain things that can get depleted, right? And I'm talking about the sacrificial anode. Once that sacrificial anode is gone, you have to basically come back and replace it, right? And you also have to make sure you constantly have to maintain it to make sure that you still have enough of the anode of the sacrificial anode to corrode. Now, when it comes down to the operation, let's say with the impressed current, right? Same thing there. Even though inert anode is something that doesn't corrode, you have to be constantly aware of other structures appearing near your structure, and you still have to maintain the pipes and make sure that you sometimes the issue with stray currents comes actually later on, something that you were not aware of. Or I also don't want you to think of this scenario where you just, well, you also have to make sure that you supply enough electrons. Right, that's the other thing. You don't want to end up with the situation where you were not supplying enough, and this is why the tank or the structure you were trying, or the pipe you were trying to protect is corroding. And another thing is that these systems, I've shown you an example with a tank and everything looks very, very simple, right? You just have a tank, rectifier, and the inert anode. But typically it's a system of pipes that are just few feet away from each other. So it does require maintenance to just basically make sure that the system operates the way you intended to operate. All right, well, with that being said, I'd like to conclude. You may read the rest, it's relatively simple and straightforward. With this, I would like to conclude the tools and techniques that you would use to control corrosion, right? To either mitigate it, the process, slow it down, or prevent its formation.